turn this on. Okay, so thank you for taking the time to come to the makeup class. What we will do is to actually, there was 1 or 2 slides from last time. I'm going to wrap that up. But today we will start a new topic and also a new chapter in the textbook. It's basically a chapter on processes, threads, virtualization, and so on. Okay. So today's topic from that chapter is going to be on concurrency in distributed systems. We will continue this topic for the next 2 or 3 classes, and then I think we'll end with virtualization and cluster scheduling and things of that sort. So it has quite a few different things. Today we are only going to talk about threads, concurrency, and thread scheduling. Okay, then we'll talk about how do you schedule at a cluster level, how do you schedule it in a cloud, and things of that sort. Though that's coming in a class or 2. So before we get started with today's topic, there was 1 or 2 slides I couldn't finish last time. Okay, we remember we were at the end of last time, we were talking about gRPC. Okay? And I said gRPC is Google RPC. It is essentially a modern RPC framework. It runs on top of HTTP, although you don't see that. You just make normal RPC calls. It uses HTTP as its transport. But the important part is it's designed to be not just platform independent. Okay? It also has language independence. So you can write your client and server in different languages. Okay? Now, regardless of which language you choose for writing your gRPC program, okay, you have to essentially have a declaration of what your gRPC methods are and what are the data structures you're going to pass back and forth. Okay? And this is essentially declared in what is called a .proto file. It's that protobuf file. Okay, last time I had showed essentially this part of the protobuf file, which is just declaring some data structure. So it's a request and a response. Okay? But now you'll see that you've added one more item to that proto file, which is the declaration of the service that you are implementing, that the server, as well as the remote procedure call. So you see that the service is essentially a greeter or a hello world service, and then you have an RPC that essentially sends back a hello response back. It doesn't, it's basically a dummy call, but that's what it does. So you declare this, then you run it through a protocol compiler, just as you did for RPC, C++ RPC. You have to do the same kind of stuff for Java. That protocol compiler will auto-generate stub code for you. That's essentially the thing that you are going to then use with your program to actually run the client and the server. Okay? So the concepts, regardless of the RPC system, are no different. But in this case, as far as the declaration is concerned, every data structure that you pass back and forth have to be declared as a protocol buffer, because you have this buffer that you're passing. You have to declare the structure of that buffer. Those are the second and the third items on that in that box, as well as the declaration of the RPCs themselves. That's the first item. Okay? And then the rest of it follows from. Okay? There is a sample code in your lablet. You should look at it. You should make sure it works for you, because lab 1, which is already out, by the way, has part 2 that requires you to implement a gRPC client and server. Okay? Yes, your question.
Take the buffer file from the program and then the writing package auto-generate the proto buffer based on data structure.
So you're asking, are there language calls to auto-direct it to the right language? Is that what I didn't understand? Oh, I see. So the protobuf is actually somewhat independent. But yes, you have to then, based on the language, you have to use that library to essentially do the right. Because it will have, there'll be a gRPC library for each language that will understand whatever the protocol compiler is going to generate for you. Okay, so that is how you are going to deal with it. So it's not like for each language you'll generate something different. The library will take care of it. Okay, so the last thing I want to say here before we move on is some additional features that gRPC supports that we have not seen in any of the RPC framework. Right? So we looked at standard RPC is one request to make a RPC call, you get back a reply. It looks like a function call. Okay? That's how all of these RPCs, RMIs work. gRPC does that, but it has 3 other things that it can do as well. Okay? So in addition to this request response interaction between the client and the server, where you make a call and you get back a response, you essentially have the ability to send more than one piece of data from the client to the server, or receive more than one piece of data from the server back to the client. And depending on which combination you use, there are 4. Okay? The simplest one is one request, get back. So you make a call, you get back a response. That's the standard. Okay? Now you have a version where the client can essentially send, instead of one piece of data item, you can send something called a stream. So you can send multiple messages to the server. Okay? And then the server will wait for all of those messages to come in, and it will process them all and send back a reply. This is called streaming RPC. Okay? You don't just make the initial call. As part of the argument, okay, you will actually say send a stream of data items, more than one. Stream essentially means more than one. So you can send all of that, get back a response. Okay? The reverse is also true. Okay? The server can send back, rather than one return value, it can send back a stream. So multiple data items can come from the server. So you make one call, multiple responses are received. Okay? And then the general case is you send from the client multiple data items to the server, and the server sends back a stream. So there is a stream going in both directions. Okay? So you have these 4 combinations that gRPC supports, which we have not seen in other systems. Okay? In addition, it also supports the notion of doing this either synchronously or asynchronously. We saw those timing charts. You can implement gRPCs as synchronous or asynchronous. So it's a modern RPC framework that gives you a lot of flexibility depending on what you're trying to do. For this course and for this lab, you'll just use the simplest version of gRPC, one request, one reply type RPCs. Okay, but keep in mind that there are lots of other features it supports, because it's a modern framework that's designed for all kinds of applications. Right? Okay. So with that, let's move on. And I'm going to talk now about our new topic, which is going to be threads and concurrency for today, but it's going to be building on this, and we'll talk about processes, virtualization, and so on next time. Okay. But first, some very simple definitions so that we are all on the same page. Okay, so you should at least know what a process is. Okay. A process on an operating system or a machine is a program in execution. It's an executing program. Okay. There's the difference between a program and a process. Program is just code. Process is that code that's actually running on a machine. Okay. Processes have address spaces, which is the memory that the OS allocates to it. And there's a control flow, which basically says what is being executed in the process. Okay? Control flow is a sequence of instructions that are being executed. That's what a standard process is going to look like. So essentially, every process has essentially an address space, and then you have the program counter, which is basically the current statement in that process that's being executed. It, of course, has other things like registers and stack and heap and so on. Okay? I'll show you a picture that essentially shows that the next slide. Okay? But now let's say, what is a thread? Okay? So threads essentially generalize this notion of a process. Okay? Now, so depending on how much you have learned about threads in an operating system, let me just ask, does anybody remember the notion of a thread? What do you think your impression of a thread is? Anybody written any threading code, multi-threading in undergrad, OS, or any other course? What is a thread? Yes.
To a process, but have access to the same memory. So you need to access harder parts of the that you're handling access to objects. Right?
Okay. So it is somewhat like a process. That's true. Okay. So first, let me explain the difference. But whatever you said is true. But I'll get to that part in just a second. Okay. So think of threads as a way to have an address space and have multiple statements or pieces of code executing within that process concurrently. Okay? Typically, in a normal process, which we call a single-threaded process, there's only one statement that's executing at any time. So you're doing sequential execution. Okay? What if you could execute multiple things at the same time? Maybe you're executing one function at the same time the same process is executing another function. Now you have the notion of concurrency because there are multiple control flows that are interleaved through the same program. Okay? That is essentially the concept of a thread. Each of these control flows is called a thread. Okay? That's actually executing some part of the code. Each thread essentially you have address space with multiple concurrent control flows. Each thread has access to the entire address space, so the thread can execute like any other single threaded process. Any function can be called, everything is shared, all the variables are accessible, etc. Okay? Each thread will have its own stack and it will have its own registers. Okay? But other than that, you share the address space, you share the heap or the code, all of that is shared. Okay? So this essentially allows us, what are the advantages? Right? This essentially allows us to have parallel execution, at least concurrent, but if you are running on multiple cores, it's actually parallel, which we'll look at as well. Okay? And the downside of doing some of this is because you have shared data that threads can access, you will need to have synchronization, which we will talk about as well. Okay? But here's a picture to show you what a multi-threaded program is going to look like. So this big box is a process, which is an address space. It's a piece of memory. Here you essentially have multiple things in there. The shaded things are essentially stacked. Okay? So each of these smaller boxes with say PC and register, that's essentially a thread. Okay? So you can think of as this thread is executing this part of the code, that other thread is executing that part of the code, this other thread is executing some other part of it. So essentially there are multiple entities within this program, which we are calling threads, that are executing different parts of the same process, the same address space. Okay? So that's the notion of a thread. Okay? Each of them has their own registers, because when you execute some part of the code, you need your own registers, copy of your registers, and then you have your own stack, so you can call other functions, you can push arguments on the stack, and so each thread is going to have its own stack, but that the code is shared, the heap is shared. You have a question? Okay. Question is, multiple things are executing within that program, they have threads. What if a result of the previous step is needed, right? So the first thing is you have to think about whether you are going to require one thread to know about what another thread has done, right? So if you are saying, what if thread B needs to know the result of something that thread A has executed? Okay, in that case, you need to use synchronization, where you might block thread B until thread A has done whatever it does and pass information. But another interpretation of what you are asking is, within thread A itself, the next statement depends on what the previous statement does. But that's standard execution, right? So you can have an if statement. You do something, then you do an if statement saying, if whatever I did has this value, do this. That's a standard sequential execution within a thread. Each thread executes sequentially, but different threads that are executing sequentially are also executing in parallel different parts. Okay? Is this clear? It is just at some level a recap, but I'll go into details because this is the part from your undergrad OS that will help you the most for this course. Okay? But we'll go through that just in case you have not done this or don't remember it. Okay? So question is, why do you want to use threads? Okay? So first thing is, machines now have processors with many cores, right? Even your smartphone will have 4 or 8 cores on it. Okay? So each standard process can only run on one core at a time because there's sequential execution. So you cannot, if you have more cores, one process that's a single threaded process cannot make use of it, right? But if you have multiple threads within a process, these threads can execute in parallel on multiple cores. So you can have multi-threaded programs that make use of all of these cores that you have on your processors. Okay? So this makes better use of hardware. Okay? So in a single-threaded world, the only way you make use of multiple cores is if you have multiple applications running. Then you can run, let's say, your browser on one core and your word processor on another core. That's how you will share the hardware. Okay? But each process cannot itself you make use of multiple core. There's only one thread. It can run on only one processor at a time or one core at a time. Okay? So that's one. Second is, switching between threads involves a context switch within the operating systems. That is expensive. Okay? But if you have multiple threads, this context switches of threads are much cheaper because they share the address space. You don't have to save the address space and load a new address space. So context switching is faster in threads. Okay, many of the calls that the threads make are much faster than the corresponding calls for processes. So for example, creating a thread and deleting a thread is much faster than creating a process and deleting a process. But you don't need to allocate a whole new address space when you create a thread. The address space is already there. You are just creating yet another thread. But if you start a new process, you have to allocate memory and load that process from disk and whatnot. So creation, deletion, switching, all of that is faster with it. Okay? Threads have full access to the address space. It's easy sharing. And as I said earlier, if you have multiple cores or multiple processors, threads give you real parallelism. Even on a single core, you will get concurrency. You will have to switch between threads, but you will get concurrent execution. With multiple cores, you will get true parallelism. Okay, so those are some of the advantages. Now let's try to look at some very simple code just to make this more explicit. Okay? This is your standard single-threaded program. No real threads in it. You can think of it as a program with single thread. Okay? So what does it do? There's a function called task. All that function does is it sleeps for 1 second, it prints something. Okay? And then here's your main program. It's just calling that function twice. It's a single-threaded process, a sequential execution. So you'll execute the task function once, then you will execute it again. Okay? Since the task function sleeps for 1 second, this is your timeline of execution. Right? So you will execute that task, then you'll sleep for 1 second. Okay? Then the task will be done. Then you'll call the second function the second time, you'll execute the task again, sleep 1 more second, and you'll be done. Okay? That's how your program will execute. There are no threads here. Okay? So let's add some threads to this program. Okay? So you have the same function task. Okay? But now, rather than having single thread of execution, we'll add 2 threads. So you'll see that you called the thread function to create 2 threads, thread 1 and thread 2. Each of those threads is going to execute that same function. So now you have 2 concurrent threads that are actually executing the same function. They don't have to, but in this case, they're executing the same function. Okay? So we'll start the threads, T1 start and T2 start. So now what is going to happen? Okay, so first thing is how this threaded program behaves depending on what the hardware is, right? Is you have 1 core, 2 core, actually the execution will be slightly different, but let's say it's single core machine, not 2 core. Okay? So under single core machine, thread 1 will run first, okay? Because even though there are multiple threads, you only have 1 processor, so you can only schedule 1 thing at a time. So you will schedule the first thread is going to execute that function. Okay? Essentially, what will happen is you will start the CPU schedule will start executing, then that function will sleep. Okay? When you sleep, essentially, that's a form of I/O where you give up the CPU, because when you're sleeping, you can't execute. Right? So you give up the CPU, then the processor becomes idle because the thread is sleeping. Okay? So then the CPU scheduler say, what else can I do? Okay, here's another thread that is ready to run. I'm going to schedule that. Okay? So you will essentially schedule the second task. Okay? And then you will start executing it. That will sleep. Okay? And then you will maybe there's some other processes that will execute at that point, and then you will be done. So that's what an execution will look like. Okay? So now essentially the I/O is interleaved. In this case, it's just sleep. You will say it's interleaved with the execution. So execution is not different in this multi-threaded process. Okay? So this is a basic concept. Whenever you have threads, when a thread blocks on any I/O, it gives up the CPU, some other thread run. This is how you get concurrency. In sequential execution, if you block or you do I/O, you wait. You can't start executing the rest of the code. You have to wait and then continue. Okay? So this is how you are going to get concurrency or parallelism. Is this clear? All right. Okay. So we'll now continue. We'll build on this and do lots of other things in today's class. But let me give you 2 or 3 definitions, and then we'll try to come back to this. Okay? So we talked about a standard process, which is also called a single-threaded. Standard process is nothing but a process with only 1 thread. That's what also, because there's only 1 flow of control. Okay? Essentially, you make blocking calls in those processes. Any calls that you have for I/O, etc., are blocking. So it's sequential execution. Typically, in a single-threaded process, there's no concept of concurrency or parallelism. That concept doesn't exist. It is sequential execution. Okay? So we looked at that. We looked at a very simple multi-threaded process. Okay, you can still make blocking calls. Remember that sleep was blocking call. That function couldn't finish until sleep has finished. So you're still making blocking calls, but you get concurrency because when one thread blocks, another thread within that process can run. So the process as a whole can make progress even if some threads are blocked, because other threads can run. In the first case, if that process blocks, nothing can run until the process unblocks. In a multi-threaded case, even if some threads block, other threads run. That was that exact example I gave on the previous. Okay? So those are the two extremes. You have something in between called a finite state machine model. This is also called event-based model or an asynchronous I/O model. Okay? An asynchronous I/O model tries to emulate concurrency of a multi-threaded process, but really uses only a single thread of control. Okay? And the way you do this is all calls have to be non-blocking. Because if you have blocking calls, then you cannot get any concurrency in a single-threaded process. So if you want a concurrency in a single-threaded process, you have to make calls non-blocking. But then if some thread wants to do something that is akin to a blocking call, you have to essentially use a non-blocking version of the call and switch to something else in that process. So this is essentially event-based programming. We are going to come back to that at the end of this class. Okay, most of this we are going to focus on multi-threaded processes. Okay, so what threads have done is they've retained the idea of a sequential execution and blocking calls, which we are familiar with, but they add concurrency. And if you run that process on a multiple core machine, you get parallelism as well. Okay, from a software engineering perspective, coding perspective, applications are easier to structure as a collection of threads than if you are using asynchronous calls, because then you have to really write your program carefully and debug it well, etc. Okay? So we'll look at this in more detail. Are there any questions on this? Okay. So let's take some examples, okay? And then we'll start building on. So where would you use a multi-threaded application? It turns out that almost any application you have on your system essentially has become multi-threaded because your system itself has multiple cores. So it's a better way to write your application. But let's think about some example, right? Web browsers. Okay? How will you take a web browser and write a multi-threaded process in it? Okay? So to understand that, you should say, okay, what does a browser do? And let's first assume it's sequential, single-threaded. Okay? So let's say a user says, I would like to click on a link. Okay? That means you want to visit that web. Okay? If you have to do this sequentially, what is going to happen? You will make a connection to this web server. You will ask for that URL. Let's say it's an HTML page. Okay? HTML page will come back. Okay? Then the browser will start looking inside the page. Maybe the page includes some images. Okay? Then it will make a connection back to the web server saying, get me the first image. And we'll download that image. Then we'll say, oh, here's another image. We'll make another connection. You'll get the second image, and so on. Okay? And after you downloaded all of these components, only then you'll start rendering the page. Okay? Then the page will actually show up on the user screen. Okay? This is how you do this sequentially. Okay? Now you can imagine the user is just sitting there. They clicked on a link and your browser is making one connection after the other, downloading HTML, downloading image 1, image 2, image 3. And then after all of this done, you can show the page. Okay? So that might seem slow to the user. Okay? How will you speed this up? The answer is with threads, but then what will you do with these threads? What are these threads going to do? Sorry, can you speak up? Okay. So you could use threads to parallelize or may do things concurrently. So for example, you might have one thread that makes a connection to the server and gets the first HTML page. Then you process it and so there are 5 images in here. Why fetch them one at a time? Well, you can just start 5 threads and then 5 threads make a connection to the server. Each one starts fetching 1 image at a time. So now you parallelize the download. Okay? If you have enough bandwidth, those images will actually download faster because you can use all of the connections speed that you have. And then you can have yet another thread. As the web pages are downloading, it already starts rendering the page. So some part of the page already shows up. As each image is downloaded, it starts rendering that image. So lots of things actually happen in parallel, and then your speed that is perceived by the user of a page load goes up. Okay, simple example, right? But now you can think about how you can use threads to do things like this, right? So that's one example of a client, okay, how you can use threads in a client, because browser is the client. Okay. Now let's take a server, which is where these threads are actually going to give us even more benefit. Okay. So what's a server do? A server, as we talked about last time, let's say it's using sockets or RPC, is simply a process that is waiting for requests from the client. Okay. Client sends it a request, server processes the request, sends back a reply. That's what any server will do. Okay. Let's again take single-threaded server. Okay. What is it going to do? It's going to essentially wait for a request. Okay. Request comes from client one. We'll take that request, process, send back a reply. Okay. While it is processing that request, if another client sends a request, what is going to happen? Okay. So you can keep the request in the queue. Let's say you don't decline it. So essentially, if other requests come in, they're just going to wait because there's only one thread. It's busy trying to work on some existing request. So until it's done, these other requests wait. So you have requests coming in, they sit in a queue. This one thread is going to process a request. When it sends back a reply, it'll pull the next request from the queue, it'll process it, and so on and so forth. So if multiple requests arrive more or less at the same time, they'll just have to wait to be processed in order. Okay. So now you can easily see how you can use threads to make this whole thing go faster. Okay. So that is what is shown in this picture here. That's a standard picture of any server-related process. So what happens when you have a multi-threaded server is you have a master thread, which we'll call a dispatcher thread, and there'll be a set of worker threads. Okay. So the master thread is waiting for requests to come from the clients. Okay. Let's say request one comes, then you might either create a thread, or if there's an existing also, here, go execute this request. So that thread goes off and executes that request. While that thread is working on that request, if now a new request comes, okay, the dispatcher can run a separate thread, okay, and then it can take that request and give it to another thread. So there's no need to wait to start serving that request until the first thread is done, because this is a different thread. It can do things in parallel while the first thread is still waiting on, not waiting, but is processing its request. Okay. So each thread can process its own request from the queue, and you still get some benefit of concurrency and parallelism and so on. Yes, question. Yeah. The question is there a limit on the number of threads, and what are some drawbacks and so on? We will talk about that in more detail. But in short, the limit, there is no real limit on the number of threads you can create. The real limit is based on how much memory you have on your system. With each thread requires a little bit of extra stack and so on. Your process size keeps growing. There's a little bit of overhead of switching between threads. So long as you have enough memory, you can create lots of threads. Okay? But what we'll come back to, what is the right number of threads you want to make in a server and so on. Okay? All right. So that's a multi-threaded server. So now you at least start getting some sense of how threads can help improve applications that we are building, add concurrency or parallelism. Okay. All right. So we'll keep that in mind. And now we will try to design that server I talked about in several different ways. Okay. You'll see that there are many different ways to build that server I just showed you. Okay, that box. Okay. This is called concurrency model. Okay. What type of threading are you using within that server is going to be it's called a concurrency model. Okay. And we'll see several concurrency model. Okay. By and large, all of this concurrency model use the same abstract representation of the server. A server is basically an infinite loop. Okay. All it does is an infinite loop is you wait for a request, you process that request. This is going to be called an event loop. Okay. Every server that we will talk about mostly in this class is essentially going to do this. It's going to sit in a loop. It will wait for requests. As each request comes, it processes it. Now, how it does this is actually going to be basically based on the concurrency model. So we'll see a sequence of different ways to implement that event. Okay? But they all will do by and large that exact thing. Is that clear? All right. Here's the first approach, okay, which is what we know, this sequential server. Okay? No threads here. So your event loop is essentially that exact code. Is saying while you wait for a message to come, so there's a request queue, incoming request arrive, so you wait for a message, you process the message. Okay? If multiple requests come to the queue, you are going to process them sequentially. Okay? So no threading, no concurrency here. Advantage is very simple. Disadvantage is requests will queue up while one is being processed. Okay? This is going to introduce what's called waiting time or queuing delay. Okay? So if you have a lot of requests sitting in the queue, the one that's at the end will have to wait for a while before it gets serviced because it's first come, first serve queue. Right? So you're going to just serve them in the order in which they appear. So as the queue grows, the waiting time grows. When the waiting time grows, as a user sitting for an answer, they wait for longer and longer for the server to respond. Okay? So we don't want to do this necessarily, so we'll try to add threads to it. So here's your first example of a multi-threaded server where we took that infinite loop and added threads to it. Okay? So this is going to use for threads, and the simplest is going to use the simplest model for threads, which is called the thread per request model. Okay? So what does it? So let's look at the code, and then you'll understand what that means. So you are in an infinite loop. So you say wait for a request. Okay? When a request comes, create a new thread. There's a second line, and then that thread is going to process the request. Okay? So you pull a request from the queue, create a thread in your process, give it that request. It will go process the request, send back the reply, and the thread will terminate. So for every new request that is coming in, we are creating a new thread. Okay? And the thread is all that thread does is it will process that request, then it's done. It's going to terminate it. The main process continues to run, but the threads only live for duration of request service. Okay? The advantage is newly arriving requests now no longer have to wait like in the sequential case. You just pull them off the queue, create a thread, and say go service this. Okay? Assign to a thread for concurrent processing. Disadvantage of this is that as lots of requests come, you are frequently creating and deleting threads. So every request you have to create a new thread in this process. Okay. All right. So what can we now do that is different from this? Okay, we can change. Yes, this question. Okay, so we can change how we create threads, and we can use a different abstraction, which is called a thread pool. Okay. In a thread pool, when the process starts up, when the server process starts up, okay, before it enters your infinite loop, it's going to create n worker threads. There's a master thread, which is the dispatcher thread. Remember that picture I showed you? There's a dispatcher thread and a bunch of worker threads are pre-allocated. You created n of them. N is some number, let's say 10. There's a 10 worker thread. Okay? So now the rest of it is the same logic. You'll wait for a request. Then you will say, is there an idle thread in my worker pool? Is there some thread that's not doing anything, not actively serving requests? If so, you pick one of the thread from your worker pool that's idle and say, here, go process. Okay? So now when the thread is done processing the request, it goes back to being idle. The previous case, it was terminated. Now it just goes back to being idle, rejoins the idle pool. Okay? All right. Advantages here is you don't have to create lots of threads. You just pre-create them at the beginning, and then you use them for forever as long as the server runs. Okay? That's going to save you some overhead because there is some overhead to create and delete threads. Okay? What are some disadvantages? Okay? So sometimes you will just have idle threads sitting there doing nothing. Create lots of threads. You might have some threads that are just sitting there idle if the server is not loaded. Okay? What are other disadvantages? Okay? So now that's good. So what if you have n threads, but more than n requests arrive at the same time? Let's say n is 10. You created 10 threads, but 15 requests arrive. Okay? The first 10 requests will all get assigned to an idle thread because there are 10 threads to begin with. Now all threads are busy. The next request that comes has to wait until one of those threads becomes free again. Okay? So reintroduced waiting time. The same problem we had in the sequential server has now come back because you did not create enough threads, okay, as compared to your workload. Okay? So if your the size of the thread pool is smaller than the number of requests that are expected to arrive more or less at the same time, you will still have queuing for the request that does not find an idle thread. And those requests will have to wait until one of the threads is done. Okay. So So essentially, when more than n requests come, you are waiting. Okay? So what can you do? You can create a thread on the go, but that brings us back to thread per request model, right? That was exactly. So here there is never waiting. It doesn't matter how many requests arrive at the same time, right? In our thread per request model, because you have 100 requests come at the same time, you'll create 100 threads. Doesn't matter. You don't need to know how many requests come. It will adjust on the fly. Okay? But in our thread pool model, we need to know something about the number of requests that are going to come concurrent. So you might say, let's pick n to be large. Yeah, instead of 10, I make it 100. Then I say, okay, what if 110 requests arrive at the same time? You can never tell unless you actually really know what the workload looks like. What it is. You can make it really large. You can say, I'll create 100,000 threads. Then you go back to the problem of only 2 requests come. All of these threads are just sitting there idle and consuming resources. So it's hard to always pick the right pool size to match the workload, especially if the workload is changing over time. Okay? And in our systems that we will look at, web and others, the workload is not static. It keeps changing. The rate at which requests come keep changing all the time. So it's hard to actually pick the right n. Okay? So what do we do? Okay? So we can make the thread pool itself dynamic. You don't have to make it static. Right? So we said n was fixed. Why does it have to be fixed? Right? So you can say, let's change the size of n depending on the number of requests that are coming. So how will we do this? Okay, so you'll say the reason you have to do this online services see dynamic workload, the request of a web server changes over time. So let's also change the thread pool size over time. Okay? So what we will do is we will monitor the number of idle threads in the system. Let's say you start with 10 threads. Okay? Let's say your low threshold, saying low threshold is 2. If the number of idle threads falls below 2, create some more threads. That's what you're going to simply do, right? So you'll create a low threshold. You'll monitor how many threads are actually not doing anything. And if that number starts shrinking, you'll say the workload is increasing. I may soon run out of threads and then requests will have to wait. So I'm going to create some threads on the fly. And I'm going to increase the size of n so that the number of idle threads is always about some threshold. Okay? And you have to also do the reverse, because you might have a scenario where there's a burst of requests. You created a lot of threads, and now they're all sitting there idle because now the request load is going down. So if the number of idle threads exceeds the high threshold, and you say I have too many idle threads, I'm going to kill some of them. So I can keep varying the n. It's not that you just keep increasing it. When there is not enough load, you decrease it. When there is higher load, you increase it. Okay? This is called dynamic thread pools. Okay? But beyond that, the code is the same. Okay? It's the same thing here, except that somewhere in this while loop, you will also have to add additional code saying, should I create more threads, not just service threads. So you will keep changing the number of threads in the pool while requests are being serviced. Yes. Okay. Question is, what is the static for the static thread pool? What is the size of n? Is it configurable? So for static thread pool, it's a configurable parameter at startup time. After that, once the process starts up, you can't change it unless you terminate the server and restart it with a bigger n. Okay? In a dynamic thread pool, there is no configuration parameter. The n will keep changing over time as the workload is going to change. That clear? Okay. So we are making the server more and more sophisticated. Now, all of these are threaded servers, but you see that there's no one way to write it. Depending on assumptions, you'll have very different ways to write it. Okay. The last one I'll talk about here is what is called an asynchronous event loop model. In this case, we are not actually going to use threads. We will use a single threaded process, but we'll emulate concurrency. Okay. The way we do this is by using non-blocking I/O. Non-blocking I/O means if you try to, let's say, do print, you try to read a file, you try to put sleep, all of that causes the program to block until I/O is complete. In the non-blocking version, you just make that request, but the program can continue execution. That's what non-blocking is. So all of the calls that you normally think about, where you do I/O, you read from a file, you read from a socket, you put a sleep, you do print, those are all blocking. Okay? And they will all cause that thread to block. Okay? In this case, if you're single threaded process, the entire process will block. And if you want to do concurrency, with a single threaded process, you have to make them non-blocking. So what that will mean is every blocking call becomes non-blocking, means that you will send the request to the OS and do this for me, but the process can continue executing something else. Okay. In the threaded case, that thread would block and some other thread would run, so the process could make progress. Here you have to do this explicitly as the programmer. Okay. You make the call non-blocking so your code can run something else, as opposed to having the OS choose another thread. You are essentially saying, I'm going to run something else. Okay. That's the basic idea behind asynchronous event loop models. Okay. There are a couple of these examples here. So the right one is essentially the blocking synchronous version, where you call this function 3 times. Okay. Each of them is blocking, so every time you do that print or sleep, that program is going to block. So it's going to take a while. The asynchronous version, because you make that function asynchronous, essentially when you call this print, this is not going to block. It will essentially tell the OS print, and it'll try to execute the next one and say, okay, do an asynchronous sleep. And so it'll continue executing this one at a time. And as soon as each of those non-blocking calls finish, you get back a notification. Okay? That is why it's called a event loop model. And you get an event, and then you go back and, okay, that's the call I had made, which was print. It's finished now. If you need to do something because the call finished, then you take an action. In this case, there is nothing to do. So you just say, okay, it's finished, let's move on. Okay? So asynchronous programming, also known as event-based programming, allows you to write very efficient programs because you are not using threads. So the context switching of threads is all gone. Okay? So the program is more efficient, but the code is actually a lot more complex to it. Okay? Very hard to debug if something doesn't work because things are happening in random order. So there's a lot of non-determinism. Okay? But it is another way to write servers, and some high performance servers essentially use asynchronous models. They don't use concurrency using threads and whatnot. Is that clear? Okay. So I just want to show you a couple of snippets of code from Python, just to give you some notion of how this works. Most likely you will only encounter this in a lablet, but you will not really write code in the lab. But there are multiple ways to do this. But in Python, you essentially have that event loop that was the while loop. You have to call the asynchronous version of that event. So whatever is running in it is not blocking. So you'll say async io.get event loop. That essentially makes an asynchronous version of the event. So that tells the Python interpreter that whatever is happening is basically going to be asynchronous. And then you have to essentially use a non-blocking version of the call. So in this case, you are going to say call soon, and you give a function. So this will basically say that when something else makes a non-blocking call, then you call this function. So you can't call it immediately. It might have blocking call. So there are different ways you will have to write the code than when you are writing threaded code. Okay? So this is one way to do it. Another way to do it is you would make the function itself asynchronous. So you have to use the async word in front of a method that says that this is basically going to be an asynchronous function, not a standard blocking synchronous function. There are 2 or 3 different ways you will write the same code. I won't get into the details here because this is not something we want to get into, but it's something you should be aware of, that this is another way to write a concurrent, not a concurrent, but a program that emulates concurrency. Okay? Because you don't have real threads, but you are getting the same benefit because you don't make non-blocking calls in your code. Right? Okay. Any questions here? We are going to now move on to the last of our models for building servers, okay, which essentially this is a slightly different flavor of building a server. Instead of having threads within a process, the server consists of multiple independent processes. Okay, so each process is its own thing, right? You know what a process is. So our server is now a collection of processes. They're not a collection of threads within a process. Okay, so you will use a separate. The concept is very similar. A request comes in, you will allocate a process to service that request instead of a thread to service that request. So that process will go off, it will service the request, and then send back a response. Okay? So you will have a process pool, which will have a dispatcher process and a set of worker processes. Okay? Dispatcher process is the one that's going to listen for requests. When a request comes in, it will look at your process pool, which is like your thread pool. Say, is there an idle process? If so, you will go and assign that request. And then once the process is finished serving the request, it goes back to being idle. Okay, so assign a request to an idle process. Once it's done, you are going to be all set. Okay, so now there are important differences between a multi-process server and a multi-threaded server. Okay, in a multi-threaded server, all the threads share the same address space. So switching between threads is actually cheap. Switching between requests that are being served by independent threads is actually quite inexpensive. Okay, in a multi-process server, there may be two processes. Process A of the server is handling one request. Process B of that server is handling another request. Switching between them is actual real context switches, like any real context switches between application, which is more expensive to do. Okay, so that's a disadvantage of a multi-process. So there is higher overhead. Okay, but the advantage is in a threaded process, you have access to the entire address space. If there's a problem and one thread does something erroneous, the entire process crashes and whatnot. In a multi-process server, if one request does something bad, okay, only that process will crash. The rest of the server will continue to run because they're independent processes. Okay? So that's something you want to keep in mind. In a multi-threaded process, if you have a bug in one of your thread that causes some problem, your entire process might crash. All the threads will die. Right? Not so here. So here you get a process level isolation. Only that process terminates. The other processes are independent. They don't have any problem because one process crashes. Okay? So that's an advantage. You get more isolation. The disadvantage is the overhead is high. But beyond that, everything we talked about for the different flavors of threads is true here. You can start with a process per request model. Every time a request comes, start a process. Okay? Very heavyweight because starting a process can take a long time. Okay? So typically, you will not do process per request. You will have a dynamic, either a static process pool or a dynamic process that will allow you to handle this without creating the process over and over again. So both of those concepts you can use here as well. Okay? Now, the reason I mentioned this is the Apache web server, which is the most popular web server for serving web traffic in the world, actually uses by default this process pool model. Okay? It also has a multi-threaded version. So you can configure it to have threads, or you can configure it to have processes. It even has hybrid where you can start n processes. Each of those processes have k threads. So you can do that too, because you can have all kinds of complex ways you set it up. But the default Apache is actually uses multi-process model. It will start a bunch of these processes. You start Apache, it will fork off some number of processes. There will be a master process that listens for requests on port 80, which is HTTP port, and then it will hand it off to worker. Okay? So that's still a very popular way to at least build web servers, and Apache has been using that for decades now. Is that clear? Okay. All right. So very quickly, let's go through all of the server architectures we talked about, right? So we started with sequential architecture. Okay, it's single process, single thread within the process. Everything is happening sequentially. You can serve multiple requests. You can only serve one request at a time, and everything is sequential. And only way you can serve multiple requests is to make that asynchronous. That's the only way you're going to. Okay, so that's sequential. And we looked at concurrent. Okay, concurrent will mean you either have multiple threads within a process, or it's either multi-threaded or it's multi-process. Both are concurrent. Okay, has different advantages or disadvantages. But in either case, you'll spawn a collection of threads or collection of processes, either a thread pool or a process pool. And then there's a master thread that's going to assign requests to each of these thread or process in the pool. Okay, so you have now this collection of things. You can have a pure sequential server, you can have event-based server, a thread-based server, a process-based server. Okay? 4 flavors. And within some of these, you can have static pool, dynamic pool, all these flavors. We've seen now 7, 8 ways to implement servers. Okay? So one quick question is, which one is most efficient of these 4? Okay? First question is asking, what do you mean by efficiency? Right? What's your definition of efficiency? So efficiency, let's say, is just the rate at which you can serve requests. But you said something, what did you say? Multi-threaded event-based application. So why is that the most efficient of the four? Okay. So we'll get to that. So you have both threading and event. It's not that is not listed here by the way, what you said, but we'll come to that. Okay. So pure sequential can't be the most efficient, right? So we'll leave that. So that's gone. Okay. So let's come back to let's look at the last two. Between thread based and process based, which one is more efficient? Which is faster? Efficiency is faster in this. It's a bit thread based because I said process is more heavyweight. Switching takes longer, creating longer. So between process and thread based is faster than process based. Okay? Then you can say, let's say thread based and event based, which is faster? Thread based. Why is that fast? Okay. So as it turns out, it's actually the opposite. The event based is more efficient than a thread based because in event based, it's only one. It's like it looks like a sequential process. There is no switching between threads. Okay. So what you're doing is you're jumping from one function to another within the same thread. There is no context switching at all in there. That is what event calls you to do. As soon as there's a notification, you basically jump to an event handler, you start executing some function and so on. Okay, and so on. So from a pure efficiency standpoint, event-based servers are the fastest in terms of pure efficiency, okay, than thread-based. Okay? But there's one problem with regards to what I said. Okay? If you have more than one core on your machine, okay, thread-based will give you true parallelism. You have two threads that will run on two cores, you will actually process twice as fast than an event-based, which can only, by definition, run on one core. Because it's a single threaded process, right? So event-based servers cannot take any advantage of cores because it just looks like a sequential process. But on one process, one processor, event-based is going to be faster than thread-based. Thread-based is going to be faster than process-based. Process-based is going to be faster than pure sequential. Okay. But now if you have multiple cores, thread-based is going to be faster than event-based. So then you can do what was just suggested here. You can combine the two. Okay. You can then say for each core, I will have one thread that dedicated to that core, and that thread is going to do the event-based process. You will not create a large number of threads. If you have 4 cores, you will create a 4-threaded process. Each thread is going to run on one core and is going to do event processing. So this is basically saying I do event processing on multiple cores. Okay? So you can combine thread-based and event-based and get the most efficient even on multiple cores. Yes, but that was not listed here. So that is really how you would build efficient server on multiple cores. Okay, so you can combine the advantages. So that should tell you something about what the efficiency of these things mean and so on. Right? Any questions here? Okay. So you will most likely just stick to thread-based in this course in terms of your labs and so on in the lab that you will see. Okay? But keep in mind there are all the other models as well. Okay? Let me also say something about parallelism and concurrency. I've been using this term. Just your question. The question is process-based and thread-based also a good combination? Is that your question? Okay. So you could have process-based servers. Each of them have threads. In fact, Apache does that. Okay, so you could have that model, what you just said. It's not going to be faster than event-based because both process-based and thread-based require you to switch between threads or processes. Okay, because there are multiple threads, multiple processes, you've got to switch back and forth and make sure each thread gets to run or each process gets to run. This context switching is where the overhead comes in. Event-based has no such overhead. Event-based is just single, it's like a sequential process. There is no switching overhead. There's just that process running. Okay, so in that sense, it's still going to be faster than any combination of thread-based or process-based or some combination. Okay. Okay. So coming to this slide, I've been talking about parallelism and concurrency. Yeah, I've used these words in the lecture. It's at least important you understand that they don't mean the same thing. They seem like this. Concurrency and parallelism sound similar, but they're actually not the same at all. Okay. So this slide is simply trying to explain what it is, what the difference between the two. Okay. So concurrency essentially means you can handle multiple requests. One request does not have to wait before the previous request finished. That's what concurrency. Sequential means one request has to wait before the previous request finished. That's what sequential processing. Concurrent processing means I don't have to wait until the previous request finished. Processing of this request can begin even before the previous request. That's what concurrency means. Okay. Parallelism essentially means I can simultaneously process requests on multiple cores. Okay. You can get concurrency without any parallelism. Okay. The way you can get concurrency on a single core, because you can run multiple threads. What will happen is you'll start processing a request, but before it has finished, you can switch to another request, do some processing, and come back to the previous request. So you can switch back and forth between requests and keep processing them little at a time. So it's not pure sequential processing. That's still concurrent. It's not parallel because at any time only one request is getting serviced on a core. Okay? Parallelism means you actually have multiple cores, so you can actually run them in parallel. So you are having two requests that are getting serviced in parallel at the same time. Okay? Concurrency means I'm switching back and forth between requests, so each of them makes progress, but you don't have two of them running at the same time. Okay? In parallelism, you can have two or more running at the same time. So they are different concepts, and you should know the difference between these two. Is that clear? Okay. So what you want is parallelism, but parallelism requires that you have the right hardware. For a single core machine, you're not going to get it. You have to need a multi-core machine, and then you need the right type of server to actually run on that machine of all the types I talked about. All right. Okay. So let's now switch to the third part. We have about 15 minutes left. So this one is going to be a very quick overview of thread scheduling, just as a way for you to understand. We talked about all of these threads and whatnot. Underneath, what's actually happening from an OS perspective. How is the OS running these threads? How does it actually make sure they run efficiently and so on? So you've got to actually dig into the OS to understand this. It's not just about writing applications with threads. As a systems course, you need to understand how the threads actually run on your machine and so on. So that's what we are going to talk about for the next maybe 15 minutes. Okay. So here, to understand how threads are scheduled, you need to know how threads are implemented. Okay. In this class, you're not going to implement threads. You're going to use threads to write servers and clients, but you have to at least understand how they're implemented to make the best use of them. Okay. By and large, any threads package falls into one of two categories. One is called a user level threads package, and the other is called a kernel level threads package. Okay. So what do these two things mean? Okay. In the user level threads package, the thread abstraction is implemented by a user level library. There's no OS support, or you don't actually use any OS features to implement threads. All of this is done as an application level library. The OS is unaware of the presence of threads. Okay. That's what it means. So why would you do this? What does it give us, or what are some limitations? So one advantage is of a user level threads is you don't actually need any kernel or OS modifications to implement threads, which means that you can write threaded programs even if the OS has no support for them. There are many operating systems that are not designed to implement threading. So then for those OSs, you can only write sequential programs by default, unless you have a users level thread library, which implement threading features at the application level. Then you can still write multi-threaded code in that case. Okay. So no OS support needed to implement threads. It is efficient because thread creation, deletions are all library calls. They are just calling the library that's part of the application. That's very quick. So it's a function call within. To create a thread, you make a function call to the library. Okay. There is flexibility because now the library itself has to decide how threads are scheduled. But you can have different library that implement different scheduling algorithms for threads. Okay. So you can pick the one that works best for your application. So the thread level scheduling policy can change depending on which library you use for your application. Okay. As opposed to the OS scheduling policy, that cannot change unless you actually recompile the kernel and modify the code. You are stuck with whatever the OS designer have chosen for you. But here you can pick what the threads use. Okay. Disadvantages of this approach are, since the OS is not aware of the presence of any threads, it sees every process as a single threaded process, even if they actually contain user level thread, because it cannot look inside a process and know that process has threads and this one doesn't. Threads are a user level abstraction. OS doesn't see it. Okay? So what does that mean? If any of the threads in your user level threads application make a blocking call, okay, let's say they print something on the screen or they try to read or write from a file, the entire process will block, even though there are other threads that could run. Because OS doesn't know that there are other threads, so hence the process can continue execution. In a normal multi-threaded process, if one thread makes a blocking call, that thread blocks. The process and other threads can run. Here, that's not the case, but the OS doesn't know, right? So it will just block the entire process. Okay, and furthermore, a user level threads package cannot take advantage of multiple processes or multiple cores, because again the OS doesn't see them, so it can't explicitly schedule one thread of that process on one core and another thread on another core, because it doesn't see threads at all. Those are all user level abstractions that are managed by user level. Okay, is that clear? Okay. So next, here's a picture of what I just showed you. Okay, so these are processes are in these smaller boxes. Okay, what you see is a library. Those round circles are essentially threads. Okay, and your OS scheduler. As far as the OS scheduler is concerned, each of this process, which has, let's say, three and two threads inside the OS, it just looks like it's a single threaded process. That's what it looks like, because it doesn't actually see these threads at all. It just sees this as a process that has a single thread of execution. And then you see that these two threads have been actually mapped to two processors. So two of these processes are actually executing because you have essentially run them on those cores. So what happens is the OS picks a process for scheduling. OS says, let's run this process on a processor. Then the threads library says, now that the process is running, which of my thread should actually execute? It's a two-level scheduling decision. The OS picks the process and the library picks the thread. Okay, because the OS doesn't see the thread. So the library has to decide which of these thread runs whenever the OS picks the process. So there are two levels of scheduling decisions. Okay, is that clear? What I just said? So the OS is going to pick one of these processes and say you run on that processor. The thread level scheduler, which is called the library scheduler, say I will pick one of these threads to actually run on that code. All right. So next is kernel level threads. Okay, as the name kernel level threads suggests, okay, everything here is the opposite. There's explicit support for threading at the OS level. The OS is involved in the creation and deletion of threads within a process. It explicitly can see that this process has these many threads, and it can explicitly schedule threads directly onto cores, because it actually has explicit support, okay, as opposed to user level threads where none of that was possible. Okay, so all the advantages of user level threads now become disadvantages here, and disadvantages of user level threads become advantages. Okay, so essentially, you are no longer able to pick a scheduling policy like you could do in user level threads, because you are bound to the OS level policy. OS picks which process and which thread within that process gets run. You don't get to decide in the application. Okay, creation of deletion of thread is more expensive than user level because it requires you to make an OS system call. When you call thread create in a library user level library, you just make a function called the library. Here, thread create is a system called to the OS and create a thread for me, and the OS will actually create explicitly a thread for you for that process. Okay, so thread creation deletion more expensive than user level library. Okay, scheduling, you no longer have a choice. But some of the other advantages are you can get true parallelism. Your OS scheduler can say, I can schedule two threads of the same process simultaneously on two cores, which is what you see here in this example. You have the same three processes, same number of threads, but you'll see that now the OS can see all of them. You'll see that each of these threads has a box in them, and it's chosen two to run on the two cores, and it's actually picked two threads of the same process to run. So this is true parallelism, where the same process has two threads executing on two different cores, so there are different parts of that process executing on two cores. Okay. which you couldn't get in user level. Is that clear? Okay, so as far as scheduling is concerned, here is OS level scheduling and so on. Questions on this? So let's now take an actual example, okay, and try to understand how all of this is going to work. You have to work with me to understand how this works. So here you have a CPU scheduler that's just going to do round robin time slicing. So it's going to take something, it'll run it for some time, and it'll switch to something else, run it for some time. So it's called time slice. That's how a CPU scheduler for an OS works. Okay? So we have a program that's sequential. It has two functions, foo and bar, green function and the red function. Okay, so how is this going to run on this CPU scheduler? So if it's a single threaded process, this is what is going to happen. Okay, first you are going to execute, because it's sequential, you'll first run foo and then bar. So the way you will do it is you'll start executing the foo function, but you will give it a time slice, which is one of those squares that you see. When the time slice expires, okay, you could run some other process, but let's say you get picked to run the same one. So you will essentially run the next time slice and so on until the green function is done. Then you will give some more time slices to the red function, and then the program will complete. Okay, that is sequential execution using time slices. Okay, now let's say that foo and bar are actually threads. Okay, you created two threads for this process. Okay, one thread is running the green function, one thread is running the red function. How is it going to execute? Okay, so we'll first start executing excuse me, the first function. Okay, so you run it for one time slice. The green runs for a time slice. Once the time slice expires, you go back to the OS scheduler saying, what should I run next? Because you're doing round robin, you will pick the next thread that is waiting to run, which is the red thread. So you will run the red for a time slice, and then you will go back, you'll run green, red. So you'll essentially interleave. The single core, so you see that now both threads are making progress, as opposed to in the sequential case, the red thread has to, not the red thread, the red function has to wait until the green one is complete. Here, both of them are actually executing. Okay, they're interleaved. They're not executing in parallel, because at any time there's only the red or green, but there's interleaving that allows each of them to make progress. Okay, is that clear? Okay. So now let's add some IO to the functions. Okay, let's say between foo and bar, you have some print statements. Print statement is IO, blocking calls. Okay, so what happens in this case, if you are going back to the sequential execution, okay, you will essentially start executing the green, okay, for a time slice. Then you do IO. When you do IO, that process is going to block. Okay, the thing will run on the CPU. If there is some other second process, you can actually run them. But if this is the only process in the system, CPU will be idle. Okay, it doesn't have anything to run because the IO has to complete. Okay, so once the IO completes, then you will run another time slice of the green and so on. Okay, so you will see that because there's IO, the green function blocks for a while, then it runs again, blocks for a while, runs again. That's how any program will run. It'll run for a while, it will block on IO, then execute again for a while. Okay. Now, what happens if you make that threaded? Okay, that was a sequential case, but if foo and bar were essentially two threads, what would happen from the CPU scheduler's perspective? Okay, so you will essentially execute green, and the green does IO, green will block. You go back to the scheduler, it'll run whatever is willing to run, it'll run red, and so on. Okay, so you'll go essentially do, so you'll essentially get from a CPU's perspective this type of behavior, but there is IO also happening, and so you'll see now that what you actually get is this. So you'll have the red, so the green runs, it blocked on IO, you run the red, it runs for a while, it's blocked on IO, but in this case, we assume magically one thread blocks on IO, the other thread's IO has finished. If it's not the case, then both threads will just wait. But here, since they're finished, you can, the green is finished, you can rerun the green and so on. Is that clear? Okay, there's one more case. Okay, what happens when you run these on two cores? This is all single core execution. If I had given you two cores, two threads with IO what do you think will happen? Both will run in parallel, and then what happens after that, after the first time slice? Okay, so both will do IO, right? So here's what you will see. So you'll run the red and the green on each core. Okay, you'll run for a time slice. They both do IO. Both cores become idle because they are both blocked. If there's some other processes running, you can run them. But here we are not assuming any other process in the system. So you just wait for the IO to finish, then both red and green run again. IO, both red and green again, and you're done. Okay, so that's how scheduling will change exactly what is happening underneath. Depends on the threads, depends on the cores, and so on. It's important to understand some of this, because if your threading code doesn't work as is, you have to understand what might be actually happening underneath. So this is good to understand. Is that clear? All right. So I just have one or two more slides, and then we will end it here. There's a interesting system that was designed called scheduler activations. What that tried to do was it took user level threads packages and said, how can we overcome the limitations of kernel, the fact that the kernel is not aware of them. Okay? So what they did was they allowed the user level threads library to communicate with the OS. Okay? Typically, we assume that for when you have user level threads, the OS does its own scheduling of a process, and the user level threads package schedules the threads. The two are not talking to one another. Each makes its own independent decision. Okay? And sometimes that works at cross purposes. One thread blocks, the entire process blocks at the OS. Okay? So to prevent that from happening, you essentially can say, let's have the user level scheduler and the OS scheduler communicate with one another, so they actually know what's going on. Okay? In particular, you might have a scenario where you have mechanism to pass information back and forth. That mechanism is called scheduler activation. So essentially, you can notify the user level library of kernel level events. The user level library can also communicate with the OS level scheduler. Okay? And the idea is, if a user level thread blocks, okay, normally the OS scheduler will say, this looks like a single threaded process, I'll block the entire process. But if the user level threads library has told the kernel saying, don't block, if you see a blocking call, let me execute something else, then you can essentially get the benefits of what you had in the kernel level. Right? So you can use this information exchange between the OS and the application to emulate kernel level thread like features using just user level. That's the basic idea behind scheduler activation. Right? There's a paper here, but I won't go into too many details. The main idea is for you to understand that since you have schedulers both at the OS level, sometimes in the user level, you can actually build something that coordinates with one another to get better scheduling overall. Okay? That's really the basic idea. Yes, question. So are you saying it only does it work only if you have multiple threads? Is that the question? I didn't follow. Okay. Yeah. So question is, does it have to be faster than the kernel level? So here the idea is you don't have kernel level threading support. So you only have user level threading support. And since there are disadvantages of doing things at the user level, how do you overcome those disadvantages? If you have kernel level support, you just use it. You don't build a user level library and try to add complexity saying, let's have the two coordinate, just do things at the OS level, you're done. So here, this was just a user level package that you are enhanced to get kernel level scheduling like features. That's what it is. So it doesn't have to be any faster. It's just emulating it. That's what the idea is. Okay. So very quickly, I think we have run out of time. I'm going to say one thing and basically end. So there is essentially a hybrid entity that sits between what are threads and what are processes. They are called lightweight processes. Okay? Lightweight processes, as the name suggests, somewhat look like a process, but also somewhat look like a thread. So they try to bring advantages of both. So essentially, in a lightweight process, you have a process, okay? And then rather than creating threads, you create within that process lighter weight processes. Okay, so each process has some collection of LWPs, which are called lightweight processes, and threads are then mapped onto these lightweight processes. Okay, so essentially, it is another way to combine user level and kernel level schedule. That's the way to think about it. Scheduler activation is one approach. Lightweight process is another approach. It's best shown with a picture, and then we will end here. Okay, so you will see now that essentially you have processes. They have library scheduler just as you had user level threads scheduler. Okay, so you have a user level scheduling framework. Okay, now as far as the OS is concerned, okay, it doesn't see this entire process as a single threaded process. It sees this as each process as a collection of lightweight processes. Okay, so think of them as each process has some smaller processes in them. Okay, so in this case, you will see this process has 2 lightweight processes. This process has 2. This process has 1. Okay, so you can have varying number of lightweight processes within them. Okay, and then all the threads within that process are mapped to a lightweight process. Okay, so this gives us back the 2-level scheduling scenario where the OS scheduler will pick a lightweight process to run for a process. Okay, and the user level scheduler will say which of the threads should I run when this lightweight process. Okay, and the interesting thing here is you can decide as a programmer how your threads map to lightweight processes. Okay, you can say, I take these 3 threads, they map onto the first lightweight process, these 2 map onto this, or you can create 1 lightweight process per thread. You can do all kinds of things that give you advantages of exactly what a kernel level thread package does, or that looks like a user level or somewhere in between. So there's a very flexible mapping between threads and essentially schedulable entities, which are lightweight processes. Okay, so this is another way you're combining OS level benefits and kernel level scheduling benefits. So it's a hybrid scheduling, again 2-level, user level and kernel level and user level, but the programmer now has control. So you can decide how many lightweight processes to create. So this process has only 1. So this looks like pure user level thread scheduling, because every time you can only run one of these things on the core, and then one of these threads has to run. That's what user level did. Okay? This looks a little bit more than that because you have 2 of them. Yeah. So you can pick both and they run, and 2 threads are running in parallel. Okay? And you can, if you had 5 of these in there, like 5 threads and 5 lightweight processes, you have 1-to-1 mapping. That's kernel level scheduling. Okay? You got the same thing. Every time you pick a lightweight process, the corresponding thread. Okay? So this is a framework that allows programmers to exercise control or how much concurrency you need, how the OS should schedule things, and so on. Okay. More advanced way of implementing threaded applications that takes advantage of scheduling features and so on. All right. So we ran over time a little bit. Let's stop here today. No class on Monday, obviously holiday. Next class is on Wednesday. Okay. And also I announced on Piazza that we will not have a class on Thursday. Okay. Thursday is Monday's schedule. So technically there was supposed to be a class. Monday's class was moved to Thursday, but because we had this makeup class, Thursday's class is cancelled. So next week only 1 class on Wednesday. All right. Okay. So let's stop here. Again, thanks for coming, and I think we'll see you all next week.